Hello. Uh, I hope I'm audible. And this is the fourth tutorial of the course Measure and Integration. So, let's start a problem, which we'll discuss mainly problems on measurable functions and convergence of measurable functions. Okay. Uh, okay. So let's. Uh, I'll discuss some problems. So let's first find a problem basically. So first I'll say what is measurable space, that little bit. Then I'll start. So let X be a non-empty set. Let X be a non-empty set, and let S be a sigma algebra of subsets of X. Okay. Now in that case we say X comma S is a measurable space, and elements of S are called measurable set called measurable sets. Okay. Now if we give a measure mu on this measurable, if we give a measure mu, that is extended real valued function on the set S, so then that will give a that will also be a measurable space like this. Okay. So now a function or extended real valued function an extended real valued function function f from x to r is called measurable if for any a belongs to real number, f inverse of, this is sometimes written class infinity, f inverse of this is sitting inside the measurable set x. Okay, s. So then f is called measurable functions, and this fact is equivalent to the fact that f inverse of a to plus infinity belongs to S. This fact is equivalent to f inverse of minus infinity to a belongs to S. This is equivalent to the fact that f inverse of minus infinity to a belongs to S. Okay. And now if in addition f is not extended real valued functions, that means what is mean by extended real valued function? That means f is taking value in the uh, if is extended real valued function, that means f is taking value, if can take value plus infinity minus infinity. Okay, this is what means the extended real valued functions. I think my network is very slow, so it is not moving smoothly. Let me check once. Okay, so now this is now if it is just real valued function, that means f is something like that, f is not taking value plus infinity or minus infinity. So in that case, f inverse of, just instead of this a plus infinity, we have to consider, here it is considering, we are considering this one. So in that case, you have to consider a infinity, this one. Okay, so this is means the a real valued function, measurable function, and f is called, if if f is defined from, if x is equals to, if the set x is equals to Rn, where n is a natural number and R is the real set of all real numbers. So in that case, we know this Rn has a natural measurable sets. Okay, Rn has a natural measurable space structure, and what is that? That is the Borel measurable space structure. That means collection of all Borel sets that is serving as the role of all sigma algebra. So in that case, if we consider this and the sigma S is equals to the Borel sigma algebra, Borel sigma algebra, note that x can have, I mean, if I consider x is r to the power n, that means one can, for easy for to understand easily, one can consider x is just real line. So in that case, one can consider the measure s is equals to the Borel measurable sets, which is generally denoted by Bn, set of all Borel sigma algebra. Borel measurable sets, that is Borel sigma algebra. So in that case, one can consider this and a function f from r to the power n to the extended real valued function. So that can be written like this way: plus infinity minus infinity. So if this function is said to be Borel, in that case, this function is said to be uh, measurable with respect to this structure if f inverse of every this type of set is actually sitting inside the Borel sets. Okay, but one can also take x is equals to r to the power n and a sigma algebra is sigma algebra, then f inverse of then f from r to the power n to r union this plus infinity minus infinity, and in that case f will be with these settings, with this setting, this is one setting, this is second setting. So with these settings, f is said to be measurable if f inverse of every this type of set is sitting inside S. Okay, and it is known that Borel sigma algebra is the smallest sigma algebra contained. Borel sigma is the smallest sigma algebra of R to the power, or R to the power n, or one can consider it is R. So Borel sigma is the smallest sigma algebra. So any sigma algebra one can consider on R to the power n, that will automatically contain the Borel sigma algebra. So with this, this is this type of function. Uh, if f is measurable, then f is called, if is measurable with these settings, then f is called Borel measurable function. Borel measurable functions. So therefore, every so that means what we are saying, as if f is such that belongs to S, then f is measurable. Okay. So now, as this Borel sets, Borel measurable, Borel sigma algebra Bn, that is contained in any other sigma algebra, any sigma algebra on R to the power n, then every Borel measurable functions are Borel measurable functions are measurable. Okay, so this is the thing. So let's go to a fixed problem. So this is the basic things I'll say. This is the difference of Borel measurable and measurable and what is mean by, and it is also complete this inclusion. That means a Borel measurable function is measurable, but a measurable function need not be a Borel measurable function. So why? Suppose we are considering a measurable function. That means inverse image of this type of set actually should be contained in S. Okay, but that is not necessarily says that this type inverse image of this type of set will be contained in the Bn. Okay, that is not necessary. So that's why a measurable functions on Rn need not be a Borel measurable functions. Okay, but a Borel measurable functions is always there, and this there exists a counter example which will show that that is measurable functions, okay, but not Borel measurable functions. So that example, I think you have know that the example is known as Cantor function, I think. Okay, this is a construction, very important function, that is a Cantor function. Okay, so I will directly go to a problem and discuss that problem. Okay, okay. First problem. Let XS be a measurable space. Let f from x to r be a measurable function. Measurable function define gx 1 by fx if fx not equals to 0 and 0 if fx equals to 0. The question is so that g is measurable. So XS is a measurable space on X. Just we only know this, and but f is just an real valued function. Here it is not extended real valued function. This is real valued function. So we have to show that G is actually a measurable functions. Okay. So that means what to show that for any to show that enough to show that basically one can write. So enough to show that for any alpha belongs to real line, f inverse of a to infinity, that is sitting inside S. Okay. Okay. So this is what we have to show. So here we don't need to take this strict one. Why we don't need to take strict one? Because here function is real value, so not extended real value. Okay. So this is what we have to show. Let me think a little bit. Here the fact is given that f is measurable. That fact we have to use. Okay. So it is given that f is, oh sorry, I have to prove that this one basically, yeah. I have to prove that f is measurable. Okay, f is measurable. That is f inverse a to infinity. This is in S. We have to use this one. So okay. Now first take, not take alpha is greater than 0, greater than 0. Equals to 0 will be that I am defining. So alpha is greater than 0. So in that case, then this is a greater than 0. Okay, a greater than 0. Then what we can say here that g inverse of a to infinity. No, here g need not take value. Okay, g will not take value infinity. Okay, so this one is equals to all those x belongs to the set x such that g of x is greater than a, and this can be written all those x belongs to x such that g of x is sorry g of x, 1 minute, g of g inverse, so what, this is some y, it belongs to g inverse a to infinity, then so gy should be belongs to a to infinity. That means that means gy should be greater than a. Yeah, that's true. 1 minute. Okay, here we can use this fact as well. Here we will use the different one, that is minus infinity to a is there. Okay, here I will use whatever I needed accordingly still. So we can write, for now we can write this one. So now this can be written as minus infinity, that is a gx, such that gx is less than a, because here if I write y belongs to g inverse of minus infinity to y, then gy belongs to minus infinity to y, that means gy is less than y. Okay, so now a is greater than 0, so now we can break it gy less than equals to 0, and the union of all x belongs to x such that g of x strictly less than alpha, so this is positive right now. Okay, so that means 0 gx less than a. Okay, we can write this. So now this can be written as, now this particular set can be written as x belongs to x. Here 0 is also be there. Okay, gx can be 0. If gx is not 0, so in that situation x belongs to x such that gx is equals to 0, that means fx equals to 0. So in that situation, fx equals to 0, this is one set union, uh, x belongs to x such that 1 by fx, that is strictly less than 0, this is another set. Okay, 1 by fx strictly less than 0, another set union all x belongs to x such that 1 by fx is right in between a, this one. Okay, this is the set. So one can look at here that, just a minute, here I am a little confused. Okay, here this is breaking this part into this part. Okay, now as f is, it is known that if f is measurable, if from r union plus infinity minus infinity is measurable, then f inverse of any singleton set is also there. Okay, so that's why this set, that implies the set x belongs to x such that if x equals to 0, that means all those points for which all those points which is inverse image of 0, that is in S first level. Second is that x belongs to x such that 1 by fx less than 0, that is equals to x belongs to x such that okay, little I messed up. Okay, just a minute. Okay, let me resolve this. I have to do it myself. Gx greater than a, right? A is greater than 0, that we have taken. So that means this can be written all those x belongs to x such that 1 by fx is greater than a. That is means all those x belongs to x such that f of x is less than 1 by a, right? F of x less than 1 by a. That is equals to f inverse of 1 by a to infinity. This is the set. But as f is measurable, then f inverse of 1 by a to infinity, this is inside this, this is the measurable side. Okay, and second stage, secondly it is saying that now let alpha equals to 0. So in that case, g inverse of 0 to plus infinity, that is equals to, one can write all those x belongs to x such that g of x is greater than 0, right? G of x is greater than 0. So this can be written break as x belongs to x such that 1 by fx is greater than 0. So now when what is the value of fx such that 1 by fx will be greater than 0? This is equals to f inverse of, f can take value 0 as well, f can take value 0 to infinity. This is what it is, right? Note that first of all check this is correct, this equation is correct, because if 1 by if f of x is greater than 0, in that case only 1 by fx will be greater than 0, and this is if and only if f is a real valued function x to r such that fx is greater than 0, then 1 by fx will also be greater than 0. Okay, this is what it is the case. So therefore this is the same, this is also there, this is also there. So this is also there, and if alpha is less than 0, then g inverse of 0 to infinity, sorry, alpha to infinity, this is equals to all those x belongs to x such that gx is greater than alpha, but here alpha is alpha is but here alpha is but here okay, just a minute. but here alpha is negative. So therefore, one can write it as x belongs to x such that g of x greater than 0 union of x belongs to x such that 0 less than g of x. 1 minute. Gx is greater than alpha. Alpha is negative. Gx is greater than 0 and another is alpha less than gx less than 0. Okay, that means all those x belongs to x such that 1 by fx is greater than 0 union all those x belongs to x such that uh, alpha less than 1 by fx less than 0. Okay, so that means this is equals to f inverse of 0 to infinity and union this is equals to f inverse of 1 by alpha to infinity. Let me check this is correct or not. So alpha less than 1 by fx, that means fx less than 1 by alpha, and 1 by fx less than 0, that means fx greater than infinity. Oh, minus infinity. Okay, so this will be minus infinity to alpha. Okay, so this is what it is. Okay, so one can check this is first of all this is what we have to check only. This is what we have to check, that if y is in f inverse of minus infinity to 1 by y 1 by a, so then what it says that f of y belongs to, that means f of y minus infinity 1 by a, that implies that 1 by f of y 1 by f of y, so that means f of y 1 by f of y is greater than alpha, greater than a, first place, and second place this is saying that 1 by f of a will be less than 0. Yeah, this is correct. This is correct. So this is what we will get, and this is also there, and this is also in space. So that implies G is measurable. So this way we will solve the first problem. Okay, G is measurable. So let's go to the another problem. Problem 2. Let x and s be a measurable space. Let f from x to r be a function such that mod of f is measurable. Is it necessary that f is also measurable? What is the question? Question says that x is a measurable space and f be a function such that mod of f is measurable. Is it necessary that f is also measurable? Okay, I think the answer is no. So let me think a little bit. The answer is no, obviously. So what we know that uh, know that know that there is a subset for any know that for any a and b belongs to real number where a is less than b, there exists a non-measurable set measurable set E non-measurable set E which is subset of open interval AB. This is true for anything. Okay. So now E is subset of open interval AB and that is non-measurable. Okay. Now what we have to prove that whether F is measurable or not. That is what we have to prove. Okay. Sorry, if mod F is measurable, then whether F is measurable or not. That is what we have to prove. Okay. So in that case, if we consider a function, let F is a function from the full real line to the real number given by F. In that case, Borel measure is greater than 0. This is the not Borel measure, this is the Lebesgue measure. Okay. Given by f of x is equals to 1. Okay, let's take this is the interval AB. This is only interval AB. I am not giving the full function. F of f is from this is the x actually. Okay, so now f is 1 if x is belongs to the set E and minus 1 if x does not belongs to the set E. Then if then mod f mod f is also the same function from AB to R, and that is always mod f is always 1 for all x belongs to real number, and it is known that every constant function is measurable. Why that is the case? It is known that every constant function is measurable. Okay. Okay, so every constant function is measurable. As every constant function is measurable, so in that case, f will be also measurable. A mod f will be measurable. But why every constant function is measurable? That is, this is what I want to say. Okay. And as every constant function is measurable, and why every constant function is measurable? Suppose f is a function from x to r, and f of x is equals to c, then for every alpha belongs to real number, alpha can be greater than equals to c. In that case, alpha can be greater than equals to c. In that case, f inverse of alpha 2, f inverse of alpha to infinity, this inverse is actually will be, this is containing c, so this will be full x which is measurable. Always this x is always inside the sigma algebra, so that's why this will be inside the sigma algebra. If alpha if alpha is less than c, so that means it is not including the set. So in that case, f inverse of alpha to c infinity, so this will be empty set. Okay, and this is also inside the measurable set. So therefore f is always it is always measurable. A constant function is always measurable. Okay, this is the reason a constant function is always measurable. This is the reason. This is the reason a constant function is always measurable. Okay. Okay. So now this is the reason a constant function is measurable that we have discussed, and now so then mod f is measurable. Okay, but if is not measurable. Why is f is not measurable? Because as f inverse of 1 to infinity, this is equals to, what will be this is equal to f inverse of 1 to infinity, that means this contains the only value 1, minus 1 is not there, so this will be e, and e is not in S. Okay, the sigma algebra. So here we are considering not in S. Okay, okay, so that's why, so this completes the proof. The answer is no. Okay, so let me go to the next problem. Problem number 3. Let x s be a measurable set measurable space. Let f from x to r be a function such that f inverse of r2 plus infinity is belongs to the sigma algebra S for every rational number, for every rational number r, so that f is measurable. So that f is measurable. Okay. So it is known that it is, this is very interesting. Okay, let me think a little bit first to be clear. Okay, so it is known that for every real number r, sorry, it is known that for every alpha belongs to r, okay, for every real number r, sorry, a, let me take it as a, okay, just a minute. Okay, so it is known that, okay, let me check. Recording is going on. Okay, so it is known that for every alpha a belongs to r, there exists a sequence of rational number Rn such that Rn converges to, and also I will choose this Rn is in such a way that um, Rn is increasing. In that way, one can consider sequence of rational number Rn converges to a. Also, one can choose this sequence Rn is increasing or decreasing, that I can choose as our convenience, but whatever we need accordingly I'll change it to increasing to decreasing. So let me check first what we need right now to write increasing sequence. Now if I want to write f inverse of a to plus infinity, okay, so the f inverse for every rational number are measurable. This is real valued function, so this is enough. Now this one is equals to okay, right now main point is that I want to write, okay, then I just want to, this is the main point, then a to infinity, this one plus infinity, this one I have chosen Rn as the sequence increasing. Okay, that means this is from the left hand side going to be the right hand side. Okay, so now I can write Rn to infinity, basically intersection of this, whether this is correct or not. Let me first check this one, because 1 by n to infinity, this one is intersection n equals to 1 to infinity, this is going to be intersection n to infinity, this is going to be, no, this is not going to be, if I take minus then 0 will be there, but if I take union of this 1 by n to infinity, union of n equals to 1 to infinity, this will be 0 to infinity. Okay, so that means we have to take union basically, and here I have to take 1 by n 1 2, this is decreasing, so I will be checking decreasing then, decreasing sequence, then union of this n equals to 1 to infinity, this is correct. Why this is? So let me check this one. Suppose we have a, if Rn is decreasing, then R of n plus 1, this is greater than less than equals to Rn. So that means R of n plus 1 to infinity, this one will be superset of Rn to infinity, right? Because Rn to infinity is the more range. So as this is the case, so therefore, if we take, so that means right now this is an increasing sequence. So now for increasing sequence, if we take full union basically, mm, decreasing sequence as it is decreasing, so Rn plus 1 to infinity, that will be superset of Rn to infinity. In that case, in that case, union of Rn to infinity, this will be equals to union of, this will be equals to limit somehow. This is the limit basically. So this is now increasing sequence. For increasing sequence, what is the limit concept? For increasing sequence, the limit is actually union maybe, right? So just let me check this one. For increasing sequence, upper bound, and suppose monotonically increasing an, in that case monotonically increasing the supremum is actually limit supremum, limit infimum actually. So in that case, as this is the case, so therefore limit supremum, this union is actually limit supremum or limit infimum of an, or limit an. So that means limit n tends to infinity, Rn to infinity, this is equals to union of n equals to 1 to infinity, Rn to infinity, and whenever Rn is going to be a alpha, so this will be a. So this is what, okay? So this is what. So now as this is what, then this, and then f inverse of a2 plus infinity, this one is actually equals to union of n equals to 1 to infinity, union of n equals to 1 to infinity, f inverse of Rn to infinity. But by hypothesis, these elements are belongs in, by hypothesis, these elements are belongs in the set S. So therefore, S, as S is sigma algebra, as S is sigma algebra, so it is closed under countable union, and F inverse Rn to infinity, this is inside the set S. That implies that, that says that, that union of n equals to 1 to infinity, f inverse of Rn to infinity, this one is also belongs to S. That is similar with saying that f inverse of a to infinity plus infinity, this is belongs to S. Okay, so now we, so this is completes the proof. Okay, this completes the proof. So therefore f is measurable. This is what I have to prove, right? This is what I have to show, that f is measurable. So that is done. So now let's go to the another problem. So now problem number 4. Okay, so now just a minute, let me check some problem. Yeah. So problem 4, what it says, problem 4 says let xs be a, let xs be a measurable space, and let fn be a sequence sequence of measurable functions defined on X. Okay, converging to F almost everywhere. Is it necessary that F is measurable? Okay, so let me think about it. Is it necessary that the F is measurable? Okay, this is the question. So I think that we can create an example like this way. So what are the easy example of non-measurable functions that are the basically um, the characteristics function on that point? Okay, just a minute. Hmm. Just a minute, let me think a little bit. Sequence of measurable functions obviously need not be, I mean, if a sequence is converging to a function which is, okay, mm, let me do, hmm, okay, 1 minute. Yeah. Mm, okay, I think there it is, Pythagoras theorem will come into the picture. This is a present converges to almost everywhere. Then, okay, the answer is obviously no, but I have to create an example that I'm trying to find. Okay, so let's take um, function which is not measurable. This is what I have to define the sequence of function. Okay, so it is measurable right now. Okay, so let's take let non-complete. We have to take a non-complete measure first place. Okay, let me first find the non-complete measure. Okay, so let's take um, let X be a set. X be a non-empty set. Or this is given actually. Let it is given that X be a take. Okay, sorry. I have to start with let take X be a non-empty set. Non-empty set. Okay, take X be a non-empty set, and sigma algebra S is equals to the set X and the non-empty set empty set S. Then S is an sigma algebra. Then S is an sigma algebra because this is empty set and X is there and it is closed under union and closed under intersection and everything is there. And then X with S is a measure space. And let's give mu is a measure from this the set S to mu be and let mu be a measure on x's such that mu at x is equals to mu at empty set is equals to 0. Okay, then if x contains 2 points, if x contains at least 2 points, say a and b in x, then these are the subset of x and mu of x is equals to 0, but these are not element of the sigma algebra S. So that shows that mu this shows that x s mu is not a complete measure space. So that means what I'm saying that if we know that a complete measure space is complete if a set has measure 0, then all its subset will be in measurable elements. So that means that will be in the set of measurable. So that's why it is not complete. Now let's take a let F is a subset, is a proper subset of this is non-empty and proper subset of R. Then E is not a measurable set, For example, take x is equals to R. So this is x basically, yeah. This is x equals to R, and E is equals to 0 to 1. Okay. In that case, if we consider what is the question? Question is measurable functions defined on Ax converging to A. Okay. If we consider functions mm, that means all open set will be there. Just a minute. So Borel measurable sets will be there, but there exists a set which is non-measurable. Now if I consider the functions non-measurable, okay, just a minute. Complete measure. First of all, answer is no. This is for sure. Answer is no. But answer is yes in some other condition that I will discuss. When E is not measurable set. Mm, okay, I think I'll not. I'll discuss that in the next class. Okay. We'll discuss later. The answer is in general no. Just let me write this one. Answer is in general no. But if the measure space is complete, if the measure space is complete, then F is also measurable. So do the next part in. Okay. So let's do another problem. Problem number 4, problem number 5, I think that was the 4, yeah. Problem number 5, but it says, let Xs be a measurable space FNVS sequence will consist so that the set of all points X, um, so that the set of all points X where the sequence is not Cauchy is measurable set. Okay. Okay. So let me try this one. Let Xs be a measurable space. Oh, no, I'll do this one. Let let Xs be a measurable space. Measurable space. Let Fn be a sequence of measurable functions defined on X so that the set of all points X belongs to X where the sequence is not Cauchy is measurable. Measurable set. Okay. So what it is asking that. So what is mean by Cauchy sequence? We know that for every epsilon greater than 0 there should exist an that means we are considering the set E is equals to all those points X belongs to X such that okay, so let Fn the sequence Fn X is not Cauchy not Cauchy at the point X if there exists if for any epsilon greater than 0 if for every epsilon greater than 0 there exists if for every x greater than if for every epsilon greater than 0 there exists m and n m mx and nx such that if m x at x minus if n x at x this is greater than epsilon greater than equals to epsilon, right? That means for every epsilon greater than 0 there we are getting an point such that this holds. So that means we can write this one like this way. um, for any epsilon greater than 0 we are getting like this way. So that means let E be the set where the sequence is not Cauchy, the set where the sequence is not Cauchy. So then this set E is equals to maybe epsilon greater than 0. I have to check that for every epsilon greater than 0 x will be there if for every epsilon greater than 0 if n is not Cauchy Okay, so I have to took it like reverse. So we can do. Okay, let me sorry for the interruption again and again. First of all, find the point. It is known that note that for x belongs to x, if nx is Cauchy, then there exists then it will converge. This is what first point. Because in this is right now in real number, right? Now in real number every Cauchy sequence is convergent. Then this sequence of real number sequence of real numbers converges to some point f. Okay, some point y which is I'll take as a y which is I'll take as f of x. Okay, that for x belongs to if this is Cauchy, then this sequence of real numbers converges to some point y equals to x. Okay, now let e is equals to all those point belongs to x such that fn x is Cauchy. Okay, that means then limit n tends to infinity f of nx is equals to f of x for all x belongs to the set E. Then, or one can give him like this way. Let f from E to the E subset of R, subset of f, this is to R, such that f of x is equals to limit. This is defined by like this way, limit n tends to infinity f of nx. Okay. So now if I can prove that the complement of the set E is actually measurable, then we are done basically. Okay, and that now and one can write for x belongs to E and 0 if x does not belongs to E. Now enough to show, not to show that the set of points where Fn is not Cauchy is measurable, that is E complementary is measurable. It is enough to show that E is measurable. E is measurable. Why? Because S is the sigma algebra. Now the set E is measurable, then E complementary will also be measurable. So that means it is enough to show that E is measurable. So that means we have to show that this set E is actually measurable. This set is measurable. This we have to show. Okay. Now but note that so okay. Now, so E is those points x belongs to x such that f of nx minus f of nx okay, so now yeah, I think so now E is the set where then E is the set. Note that E is the set where Fn converges pointwise to F. Okay, okay. Now then for any x belongs to E and any positive integer p and any positive integer p, there exists a natural number k naught belongs to n such that whenever m comma n is greater than equals to k naught, then mod of f of nx minus f of nx, this is less than 1 by p. Okay, so therefore E can be written as, this is the interesting fact, a p is equals to 1 to infinity, p is equals to 1 to infinity, k equals to 1 to infinity, intersection m greater than k, n greater than equals to k, or here you can take strictly, so then we have to take here strictly n greater than k, such that x belongs to x, such that f of mx minus f of nx less than 1 by p. Okay, so this is the set. So now clearly these are the measurable set. These are the measurable set. Now now it is enough to show x belongs to x such that f of mx minus f of nx is less than 1 by p is measurable. In and then and why this is true enough to show, because if we can show that x belongs to capital X such that f of mx minus f of nx is less than equals to 2, this is the this is measurable, then this is measurable means intersection of measurable sets will be measurable, and again union of measurable sets will be, as E is actually union and this type of sets, as E is actually union and intersection. Union is intersection and union and intersection like this, in an intersection of this type of sets. Okay, so but now note that this set x belongs to x such that f of nx minus f of nx, this one less than 1 by p, is equals to f of n minus f of n, this function inverse minus 1 by p to 1 by p, and this is belongs to S, measurable sets. Why this is? As Fn and Fm are measurable for each m and n, then Fn minus Fn is again measurable. So that's why it is possible. So I mean, main fact is that Fn and Fm both are measurables. That's why this and this 1 minus p to 1 plus p is actually 1 minus 1 by p to 1 by p. This is actually minus 1 by p to 1 by p. This is actually open set. So therefore, inverse image of every open set is measurable set. So this Fn minus Fn is measurable set. So that's why this is measurable. This is measurable means this set is measurable. This set is measurable means this union intersection is measurable. This intersection is measurable means this union is measurable, and this union is measurable means the set E, that is what the intersection of this type of sets is also measurable. So this is first check. This is very important, and this is not easy just to follow the definitions, and then you'll be able to prove this. Okay, so this is all. Now we will be going towards the Egorov's theorem. You know what is Egorov's theorem and some results. So let me first go to some problem. I think already I will consider. Okay, so problem number 6. What it says, let X S mu be a measure space okay, and let Fn n equals to 1 to infinity be a sequence be a sequence of real valued measurable functions defined on X converging in measure to a real valued measurable function measurable functions f defined on X if G is a real valued measurable function defined on X real valued measurable functions defined on X such that f equals to G almost everywhere, so that Fn converges to G in measure. So what is by mean, that I know these are the already discussed in class, so still I will be discussing a little bit. So what is the question? It says that let X S mu be a measure space and Fn be a sequence of real valued measurable functions defined on X which converging in measure. First fact, this is converging in measure, that is what Kilper. to a real valued measurable function f defined on x. If g is a real valued measurable function defined on x such that f equals to g almost everywhere, then show that fn is converges to g. So now, first to recall that, a sequence of measurable functions real valued measurable functions, is converging to f in measure, is converging to f in measure if for any given epsilon greater than 0, limit n tends to infinity, x belongs to the set x such that uh, mod of f of nx minus f of x, this is greater than equals to epsilon, this limit is goes to 0. Okay, so this is what it is mean by converging in measure, and denoted it by fn converges to f in measure. This is what the sequence fn converging in measure to the function if every epsilon greater than 0, we have limit n tends to infinity mu of x belongs to x such that mod of fnx minus fx greater than equals to epsilon for all epsilon greater than equals to 0. Okay, so now it is known that now Egorov's theorem says that Egorov's theorem says that okay, so there is an important update. I think this has to be finite measure. Without that, it is not possible. So is it the measure space? It can be a sequence. Real valued measurable functions converging in the measure to a real valued measurable function defined on x. If g is real valued measurable function, finite measure space. Finite measure space. So Egorov's theorem says that. Let me write the Egorov's theorem. Egorov's theorem says that As mu of x is finite, then for any epsilon greater than 0, there exists a set, measurable set. There is measurable set f of x such that mu of x is less than epsilon and Fn converges to F uniformly on F complement. This is the Egorov theorem. So now, using the Egorov's theorem, then x belongs to, then there exists n naught belongs to natural number n naught such that mod of fn x minus fx is less than epsilon for all x belongs to, that means the set less than epsilon for all x belongs to F complement for all n greater than equals to n naught. That is mod of f of nx minus f of x. This would be greater than equals to epsilon only when, I mean, such that this will hold for all, this will be subset of f for all n greater than equals to n naught. Okay, this is very much straightforward. And then, as measure of f is E, measure of the set X, measure of this set basically, measure of this set X belongs to S such that mod of f of nx minus f of x greater than epsilon, this set is actually, measure of this set is actually less than is equals to measure of f, and that is less than epsilon. So therefore, what you can say is that measure of, and this is true for every epsilon greater than 0, just a minute. Fn is converging in measure. Okay, this is given, so that means this limit has to go 0. But the limit of this set is going to 0. That means then for given, for delta greater than 0, then for given delta greater than 0, there exists a natural number such that this will hold less than equals to delta. This will hold less than equals to delta less than equals to delta, but this is less than equals to a, less than delta, this is less than equals to epsilon. Okay, so therefore what we are getting here actually, uh, also by also by mm, okay, now we have got one thing. Okay, now we have to prove something different. Okay, here it is saying that if g is real valued measurable function defined on x such that f equals to g, that is no. Question is little different. These questions will be solved later. Almost everywhere. Then use Egorov's theorem to show that Fn converges to F in measure. Okay, so recall that a sequence of measurable functions is converging to F in measure if for any epsilon greater than 0, this is going to 0. This should happen. Okay, and so this is what we have to prove. Okay, this is what to prove. Now by Egorov's theorem says that if a sequence is converging, Egorov's theorem says that let Fn be a sequence of measurable functions which converges almost everywhere to a measurable function f, then to a measurable function f, and for any epsilon greater than 0, there exists a measurable set f of x such that mu of x is finite and fn converges uniformly on fx. Okay, so therefore, so here what we got. So then for given delta greater than 0, there exists an delta. So as by this Rigorov theorem, for given delta greater than 0, there is a natural number n such that fn x minus fx less than delta for all x belongs to f. Remember that is x belongs to capital X such that mod of fn x minus fx that is greater than equals to delta, that is subset of f for all n belongs to greater than equals to n naught. Okay, this will hold for all. This will automatically hold, and that means measure is less than equals to to change little bit. This is something getting very bad, but okay. Then by Igorov theorem, there exists a set f such that mu of f is less than epsilon measurable, and fn converges to f uniformly on fc. Okay, so we are going that way. Okay. Um, so now as this is true for every epsilon greater than 0, also as this is true for as this is true for every epsilon greater than 0 and delta greater than 0, then by definition of limit n tends to infinity, mu of x belongs to x such that fn x minus fx mod greater than equals to delta, this is equals to 0. Okay, so what is the total idea? Total idea is that suppose we are giving that fn is a sequence of functions which converges almost everywhere to a function f. Okay, then by Igorov's theorem, what we are getting that there for every epsilon greater than 0, there exists a measurable set f such that mu of f is less than 1 and fn converges uniformly on fc. Now, if I want to prove that if I want to prove that the function f is converges to fn converges to f in measure, that means for every delta greater than 0, we have to show that this limit is actually 0. Okay, now as as then for given f, as fn is converges uniformly on fc, so that means for given delta greater than 0, we will always find a natural number n naught such that whenever n is greater than equals to n, this mod of fn x minus fx less than delta for all x belongs to fc. So that means the collection of elements such that mod of fn x minus fx greater than equals to delta for all n greater than equals to n, this set is subset of f always. Therefore, measure is less than equals to mu f, but mu of f actually this mu of f, as mu of f is less than epsilon, that is given because that is what where the Igorov's theorem using, and so therefore so what we get, the measure of this set is less than epsilon for all n greater than equals to n naught, and for a fixed delta greater than 0. For a fixed delta greater than 0, so you can write this one like this way. For a fixed delta greater than 0, for any arbitrary but fixed delta greater than 0, for any arbitrary but fixed delta greater than 0 for any arbitrary but fixed delta greater than 0, um, delta greater than 0, mu of and any epsilon greater than 0, mu of x belongs to x such that fnx minus f of x, this mod is greater than equals to delta, this set has measure less than epsilon. That implies this is 0. Okay. Now I will discuss only one small problem and I will close today's session. So let me write that the problem which I have initially written, that problem that was problem number 6. So problem number 7. Problem number 7. Let x s mu be a measure space. Let fn n equals to 1 to infinity be a sequence of real valued measurable functions defined on x converging in measure to a real valued measurable function f defined on x if g is a real valued if g is a real valued measurable function defined on x such that f equals to g almost everywhere, so that fn converges to g in measure. Okay, so this is what is the problem. So now what we'll first do, I'll first discuss a theorem. That theorem says that if a sequence of real valued measurable functions converging in measure to a real valued measurable functions f defined on x, then this is almost everywhere convergence. This is what I have to prove. Measure okay, so therefore Okay, so that means what I have to prove is that for given epsilon greater than 0, if n converges to G in measurements for given epsilon greater than 0, the measure of the set x belongs to x such that mod of f of nx minus g of x, this one is greater than equals to epsilon, this set measure has to 0. Okay, this is limit n tends to infinity. Limit n tends to infinity, we need to show that this. But as f equals to g almost everywhere, there exists a measurable set f of x such that mu of f is equals to 0 and f of x is equals to g of x for all x belongs to f complementary. Okay, it belongs to f complementary. Now it is given that fn uh, fn converges to f in measure, fn converges to f in measure, that is for any delta greater than 0, limit n tends to infinity, x belongs to x such that fn x minus f of x, this greater than equals to delta, this is equals to 0. Okay, this is what it is given. Okay, now let's start from this set, measure of this set. Now this set x belongs to x such that f of nx minus gx, this greater than equals to delta, this one is can be written as union of x belongs to x such that this is subset of basically x belongs to x such that f of nx minus fx, this is greater than equals to delta by 2 union of x belongs to x such that f of x minus g of x, this is greater than equals to delta by 2. We can write this way by using the fact that x belongs to x such that f of nx minus g of nx, this is less than equals to g of x. Okay, now note that the set x belongs to x such that mod of x minus g of x greater than equals to delta by 2, this is the subset of f. Then measure of the set x belongs to x such that f of nx minus g of nx greater than delta by 2, greater than delta, greater than equals to delta, this is less than equals to measure of the set x belongs to x such that fnx minus fx greater than equals to delta by 2 plus mu of f, because this set measure is less than equals to mu of f, but this is equals to 0. So that means as limit n tends to infinity mu of x belongs to x such that fn x minus this one is greater than equals to delta by 2 is equals to 0, that implies limit n tends to infinity x belongs to x such that f of nx minus gx delta this is equals to 0. So this completes the proof. Okay, so I will stop here. I hope in the next class we will be discussing from the next.